Welcome, guys, to week number 8. This is chapter 2, but like the first one from me. So, welcome back. Haven't heard you guys in 2 weeks. Um, this chapter is gonna be about fields. You probably, if you haven't encountered it yet, can't really imagine what a field is supposed to be, but we will go over it in a minute and explain what it is. So the content of this lecture will mainly be about talking about the mathematical concept of a field, the definition, and how all the rules apply to our numbers and operations and also with each other. And then we will take a look at how something seemingly so arbitrary and well, random comes in pretty handy for the daily operations in mathematics that we are applying them to. The motivation for all of this comes from a pretty old place. So you all probably were introduced to the concepts of mathematics, addition and multiplication, just calculating stuff at a very young age, probably in primary school, maybe even earlier. And addition and multiplication were probably defined as the bedrock of anything which is math. We can add and multiply things, and this is like the smallest denominator that we can break things down to in order to solve them, right? Because whatever complex problem you have, if you break it down to addition and multiplication, this operation becomes trivial. However, these two concepts do kind of fall out of the sky, right? No one really explains you how addition and multiplication is justified. You just say, oh, all right, you are adding the number of fruits you have on a table. This is addition. Or you are, for example, calculating how much money you have won if your stock price increases by 30%. But in a sense, it's not the real human world that was out there. And then we came up with the concepts of mathematics to describe them. But there were the concepts of mathematics first. And they just so happen to accurately describe what's going on. So we need to find some kind of common ground, some kind of basic rule which defines the concepts of addition and multiplication in order to be able to properly talk about algebra. And we will do so by introducing a idea which builds on the content which you learned in the last chapter. As you remember, there is such a thing called groups. A group is nothing than the combination of a set and an operation. A set is just a finite or infinite number of elements, and a operation is, in mathematical terms, a function which maps from the cross product of your set onto the set. So you take two elements of your set and the operation maps those two elements onto one element. So in a sense, 2 plus 5 is nothing else than a function which maps 2 as an element of the group and 5 as an element of the group to the element 7, which is also part of the group. So for those basic operations, multiplying and adding, that we know, we want to come up with some sort of algebra. I mean, there are many, many different operations, right? You can come up with operations you like, and some of them may have some properties, and others may have different properties or fewer properties. But we now really don't care about this. We know that in day-to-day mathematical applications, adding and multiplying are the absolutely fundamental basics of operations, and therefore we want to introduce them into a system of numerical operation. We want to figure out how they behave when we combine them. So, for example, if we say a times brackets b plus c, how does this behave? And in order to analyze how these things work, we need further definitions. We so far have had no definitions which would cover a mathematical numerical system which contains more than just one operation. So this is just what we're going to do right now. The thing which we need is a field. In practically, we want to take our group as we knew it with one set and one operation and add another operation to it. So we want to have a group and an additional operation. However, this does not suffice because this does not cover the interplay between both operations. So in order to cover this, we have to start with a brand new definition. So it starts similar to the definition of a group. We have a set K, which is the set everything is based on, and there are two operations. The first operation is the usual plus operation, and the other one is the usual multiplying operation. And additionally, there have to be two distinct elements, a 0 and a 1, which you already have heard of in the definition of groups, that there are some special elements. We will keep the elements 0 and 1 in our mind for this definition. Okay, and so now we first of all start with getting the group properties right. So here, as you see, the first four rules are the axioms of addition. These you have already encountered in the definition of the additive group. So when you add, if you just carry out addition, if you add, you have associativity. It doesn't matter how you group the additions. You have commutativity, so order doesn't matter. And there is a neutral zero element. So there has to be an element which, if we use it in an additive operation, it just yields the other element of the addition. So anything plus 0 is the same anything. And additionally, we do need to have an inverse element, right? So there has to be something which added to what we had before yields the neutral element. Wherever we are in our space of numbers, there has to be another number which we can add so that we get the neutral element, which is, in the case of addition, 0. Here you should note that 0 doesn't literally have to be the number 0. There may be additive groups where the neutral 0 element is a different number from 0. You don't really have to put this into use right now for anything, but it's good to keep that in mind, that for the definition, the 0 element is not talking about the actual number 0, but just of an element which has the neutral property that 0 has with, for example, addition in most number spaces that we know. 0 just happens to have this property in most examples that we know. All right, but we're far from done. So additionally, we have the axioms of multiplication. As you see, we also have to have the multiplicative group as an abelian group, but here the neutral element is the 1 element. Again, similar with the axioms of addition, it does not have to be literally the number 1. It just has to be a number that has this property. And we also have to have an inverse element. So there, for every number a, there must be another number called a to the power of -1, so inverse of a, such as multiplying them yields the neutral element. So same concept as with addition. But the crux here is the third point, distributivity. This defines how addition and multiplication play with each other. So the point is, this is basically the in German we would say the Ausklammergesetz. The point is that if you multiply an addition, this is equal to adding the multiplication of every single element. So a times b plus c is a times b plus a plus c. And here I've noted it's important that this works from both sides. So theoretically, this could be an additional rule. So not only a times b plus c, but b plus c times a also has to work. There's some notorious examples where everything works, but distributivity only works from one side, and then it's not a field. It's important that distributivity works from both sides. All right, so now we have a lot of rules. And the question is like, what are we gonna use these rules for? Well, the point is, if we take a set and then we combine it with addition and multiplication, we can always just check, does it fulfill all the rules? And if it does, we call it a field. And if it doesn't, well, it's not a field. But just from the definition itself, it's pretty difficult to have a feeling for what constitutes a field and what doesn't. So, for example, are the real numbers a field? Are the complex numbers a field? Are the integers a field? Well, let's start by making an example of a very simple field. Imagine our set is just the finite set of 0 and 1. Then we can define addition and multiplication here. With a finite number set, when we get the number 2, we just take the rest of it. So we basically divide by 2 and take the rest. This would be called a modulo operation. So if we take 1 plus 1, that equals 2, and 2 divided by 2 yields rest 0. So 1 plus 1 here is 0. And everything else works exactly the same way as usual. So 1 and 0 is 1, 0 and 0 is 0. 0 times anything is 0, and 1 times 1 is 1. And here, the additive and the multiplicative groups are abelian by definition. And for the addition, you have the neutral element 0, and every element has the property that it's inverse to itself. So the neutral element is 0, and to get from 0 to 0, you add 0, and to get from 1 to 0, you add 1. So both elements are its own inverse. This is different for the multiplicative group. There, the neutral element is 1. And to get from 1 to 1, the inverse element is 1. Now, hold on, you might say, there's no way to get from 0 to 1. This is true. There is no inverse of 0. However, if you look back to the definition of a field, you will see we have added that the inverse property for multiplication does not have to hold for 0. This is very important because there's no way to multiply 0 and get 1, right? Everything multiplied with 0 is 0. We already know that. This is not in the definition of a field, but later on we will see that this property of a field is directly yielded by the definition. So we can prove that using the definition. But this special case where we say, okay, 0 does not need an inverse element, it's important in order to keep it a field. And now we could just, by hand calculate all the nine properties and see that it's a field. But we're not going to do this by hand. We just talked through it and saw, okay, this will be a field. In order to prove it, of course, you would have to calculate all the nine properties on paper in order to show it. But this goes to show that a field doesn't have to be something very complicated. A set with only two elements already fulfills all the requirements for a field. You just have to bear in mind that a field is something powerful, and there are also some rather big sets. I mean, there's some infinite sets and some very complicated sets, which nevertheless violate some of the properties of a field. The arithmetic implications of this are pretty severe. This will later on show that we can carry basically any arithmetic, which we usually would use the real numbers for. We can carry it out in the field over two elements. This basically goes to show that everything that we value and need the properties of a field for, we can calculate in any field we have. And the field over two elements is the simplest one. So it kind of gives you a lower boundary of what is possible. Of course, many things are very nasty to calculate in such a field with just two elements. There's very little degrees of freedom, and in many ways, the real numbers are much more expressive than the field over two elements. However, it goes to show that the field of two elements has the same arithmetic properties as. Now, probably the direct follow-up question you have is, well, what about the other sets, right? We have a handful of number sets which we use all the time, and the question is, which of them is a field when you put addition and multiplication into them? And for this, let's take an example. Let's take the example of the integers, which we also denote with z. These are all the whole numbers, positive and negative. They can be added and multiplied, obviously. -5 plus 8 is 3, obviously. But we do get fallout with the integers at one point, which is here simply shown on the slide by an example. Assume the number 7, right? It's an integer. And now we try to compute its multiplicative inverse, right? We know that every number except 0 has to have a multiplicative inverse. This means that 7 times a has to be 1, and there must be a number a which fulfills it. This is a trivial equation. We can simply solve it. A has to be 1 over 7. However, we are in the integers, right? 1 over 7 does not exist in a set of integers. This means, given that the integers are the set we're dealing with, there is no inverse, right? There's no way to invert the number 7. Therefore, the requirement of having a multiplicative inverse for any number in the set is violated. And this again means we can't do it. The integers are not a field. They violate this property. You could again go to show that they fulfill all of the other properties. I mean, spoiler, they do. You would have to figure it out, but violating one property is of course sufficient for it to not classify as a field. This problem obviously disappears when we substitute the integers with rational numbers. The rational numbers are the numbers which are expressible as fractions of integers, and 1 over 7 obviously is a fraction of two integers. So any inverse number there is can be expressed with rational numbers just by flipping the fraction, and the problem disappears. And thus the rational numbers are a field. And you will see if we take more complicated sets of numbers, so all the numbers with higher cardinality, like the rational numbers or the like the real numbers or the complex numbers, they will form a field as well because they're even more flexible in their arithmetic. Just one quick note, you should bear in mind that this does not generalize. There are more complicated sets of numbers than the complex numbers. For example, there's quaternions, which don't use just 2 dimensions but 4 in order to express a number, and those then are not fields because they start to violate other properties. So they, for example, are not commutative. So you can't interchangeably swap places. The order of calculation starts to become more important when you get more complicated sets of numbers. But this is just a quick side note. This is not too important. It's just important to know that the fields over infinite sets that we are going to use on a daily basis are going to be the rational, real, and complex numbers. Alrighty, so let's go over some useful properties, which are more or less the reason we define fields. I mean, they're not the reason, as these properties still existed before we defined fields, but we want to be able to justify them using fields. So the first rule, most straightforward rule, is annulation. I already mentioned it a couple of slides ago. So we want that a number of our set A times 0 is always 0. And we can now use the rule of distributivity to prove this. The proof is a little bit backhanded. So we take A times 0, and we can put the 0 in brackets and express it as 0 plus 0, since 0 plus 0 is 0 after all. And now if we use the rule of distributivity, we get A times 0 plus A times 0. And now we get an equation of A times 0 is equal to A times 0 plus A times 0. And now we can just subtract the term A times 0 on both sides. And then on the one side we have 0, and then on the other side we have A times 0. So we know that A times 0 is equal to 0. So the rule of distributivity immediately yields the property of annulation. Okay, and the second set of rules that are important to us, these ones we're not going to prove in detail, but if you feel like it, you can try proving them. They're all 1 or 2 line proofs using the definitions of a field. So the first one is that if you have a multiplication with a negative, then the negative is interchangeable. The second rule is that if you're multiplying 2 negatives, the negatives cancel out, so 2 negatives yield a positive in multiplication. And the third one is that practically distributivity works the exact same way if instead of adding, we subtract 2 elements. Okay, and a third very useful property, which we're using a lot in applied mathematics, is the non-zero divisor property. So this is always kind of a backhanded weapon we can use to kill some numerical problem. It's the simple logical argument that if A times B equals 0, then either A or B must have been 0. So the point is, if A is non-zero and B is non-zero, then their product will be some number other than 0. This intuitively makes a lot of sense, and it's a strong argument to use in many proofs. However, we don't know the proof yet, right? So now, I'm gonna thank you for sticking around for so long and ask you to, if you need it, take a small break, take a little drink, and then grab a piece of paper and a pen and try to solve the following. So here again we have the statement, which I just defined, the non-zero divisor property. So if A times B is 0, then either A equals 0 or B equals 0, or both, obviously. So you're supposed to prove this using the definition provided by slide 4, I think. So the definition of a field. And a small hint is that the most efficient proof paradigm here would be a proof by contradiction. So assuming the opposite statement and then showing that this contradicts the axioms of mathematics. Okay, back to topic right now. There are 2 more little things which I would like to mention before the end. And the first one is, what the hell is going on with integers now? So apparently integers are not a field, they violate one property, but does this mean that we cannot do math with integers? Sure it does, but there are many properties in mathematics, especially in higher mathematics, which require the property of a field, and most of these requirements are not met by the integers. So there's many applications in higher mathematics for which the integers are unsuitable. However, they only violate one property. So this means they still annulate, right? I mean, distributivity still goes for the integers. If we take 0 times an integer, it's still 0, right? So the integers still yield a powerful numerical concept. It's just a bit weaker than the one of a field. And since there are a few mathematical sets that lack this exact property, the lack of an inverse, people came up with a definition for it, and they called it a ring. So if you fulfill all properties except of multiplicative invertibility, it's called a ring. Now we're not gonna go too much into depth with rings. However, there's one further ring which I would like you to be familiar with, and this is the set of polynomials. Yes, the polynomials are not a set of numbers, they're a set of expressions. However, they still constitute a mathematical ring. Most importantly, it's the polynomials over a field. So we have the set of polynomials which take as an input a field. So for example, the polynomials over real valued x. That's important. If you think about it, it becomes pretty apparent. You can add and multiply polynomials, and it always yields a new polynomial, right? An addition of polynomials just adds the factors, and a multiplication multiplies them, plus it increases the um, the highest exponent of a polynomial, but in the end, we always get a new polynomial, right? So it fulfills all group properties. There are neutral elements because 0 and 1, the numbers 0 and 1 are also polynomials. They're polynomials of degree 0, which means that if you multiply a polynomial with 1, 1 is the neutral element. And in the same spirit, you can add a 0. And in a similar sense, you can also find a additive inverse of a polynomial. Just multiply the entire thing by -1, and then you have your additive inverse, because where earlier it was 17x to the power of 6, now it's -17 to the power of 6. So you just flip all the signs, and then you get an additive inverse. However, as you already guessed, the breaking point are multiplicative inverses. In a similar sense, here the inverse of x squared, a very simple polynomial, is x to the power of -2. And albeit a mathematical expression, this is not a polynomial, right? 1 over x squared, or x to the -2, does not have a positive degree, and thus is not a polynomial. And if it's not a polynomial, it's not a set of polynomials, which means that there is no polynomial in a set of polynomials which inverts x squared. There's no x squared times a such that our result is 1. And so in practice, we denote the polynomial ring as P of k with those pointy brackets, where k is the field of the domain. We can plug here in real numbers or rational numbers. Doesn't really matter, and these are just the numbers that supply the x variable in our polynomial. Okay, so to summarize, we saw that we need some ground rules in order to be able to confidently talk about arithmetic and algebra. And we did this by taking the groups of multiplication and addition, which we already learned about in the last chapter, and combined them with an additional rule of distributivity in order to get a numeric system called a field. And those fields They satisfy a lot of important algebraic properties, and some examples of them are the rational, real, or complex numbers. But finite sets like 0 and 1, or other finite sets, can create fields too if we add the rule that addition of two elements that exceeds the size of the set reset to 0. So for example, here 1 plus 1 is not 2, but 0. It is, for many sets, difficult to fulfill multiplicative invertibility. So for many sets, it's the first breaking point. It's the most difficult to fulfill condition. I guess there are sets which fulfill this condition but fail on others, but this is a very common one. And so if this one is failed, we are talking of a ring. It's still a powerful algebraic structure, but not as powerful as a field and therefore less used. And notable examples being the integers and the polynomial ring. And maybe an additional summary point to bear in mind is that fields are not innate to mathematics. So quite different from, for example, differential calculus. It's not something that we discovered, but it's an algebraic system we came up with ourselves just because we consider it powerful and useful. But contrary to many other aspects of mathematics, fields were not discovered, but they were invented or they were designed. Okay, thanks so much for sticking to the end. I'm gonna now quickly go over the exercise solution or a sample solution for this exercise. I bet there's many different ways to prove this, but this is one quite straightforward way. So we have that a times b is equal to 0, and if that's given, then either a or b have to be equal to 0. And if we want to prove this by contradiction, we have to assume that the opposite is the case. The opposite would mean a and b are equal to 0, but both a and b are not equal to 0. A times b is 0, but both of the factors are non-zero. And now we want to yield this into a contradiction. And the way we're going to do this is by multiplying with the inverse. So we know, since a and b are not equal to 0 individually, that there must be an inverse to a and an inverse to b. And we can just write the equation as stated here, that a times b times the inverse of a times the inverse of b is 1, just because we have a rule of commutativity. The numbers are commutative, means that order of calculation doesn't matter, and we can just calculate a times inverse a, which is 1, and b times inverse 1, which is 1, and 1 times 1 is 1. Okay, so we have figured out that this equation equals 1. However, there's a different way to evaluate it. We know the annulation rule. It says that anything times 0 is 0. And we know that a times b is 0, so we can just substitute a times b with 0. However, 0 times a to the negative 1 times b to the negative 1 must be 0. But this contradicts our finding from above, which said that, according to the definition of a field, it has to be 1. And since 1 and 0 are not equal, well, this means that the initial assumption that both a and b are non-zero must be wrong. Ergo, there must be either a or b 0. Okay, thanks for listening. Thanks for the attention. And I'm looking forward to seeing you next week. Have fun with chapter 3 by Marissa this time. Take care.